Hi everyone, welcome to part 2 in my video series, What I Think Every Adult Should Know About Science. Check out the first video first, and then join me here, or keep listening, but it's good to go in order. I am a math and science tutor. My website is achievewitheasetutoring.com. I'll do a link in the description below as well. Feel free to go to that website and get in touch if you're interested in online tutoring. I tutor anywhere in the world by Zoom and other platforms. Okay, let's get going. All right, in the last video, part 1 of this series, I started talking about what do scientists just basically study, and I said it was stuff and stuff moving, and then we started focusing on the stuff part. And that's stuff. Stuff is stuff. Stuff is what scientists call matter. It's everything around you can see, from people, trees, cars, rocks, clouds, water, and some stuff you cannot see, like air. And then I told you that if you zoomed in on any of that stuff, anything, your finger, a table, rock, a tree, and you zoomed in far enough, you would find 3 basic particles that we can think of as just interchangeable little building blocks, or like little BBs. And those particles were protons, neutrons, and electrons. Then I said that these protons, neutrons, and electrons arrange themselves in different numbers, and they make the next level up when they do that arranging, and they form what we call atoms. So now we're kind of zooming back out. Protons, neutrons, and electrons arrange themselves into atoms. There are 92 naturally occurring kinds of atom or elements, and they are found in the famous periodic table. Don't worry why it's called periodic right now. These 92 elements are just combinations of protons, neutrons, and electrons. So everything we could say is made of protons, neutrons, and electrons, or we could say everything is made of the atoms that are made of protons, neutrons, and electrons, and there's 92 of these atoms. So I want to emphasize this arrangement idea. It's how these just 3 building blocks are arranged and combined that makes all the difference. So again, if I've got 6 of these protons arranged with 6 neutrons and some electrons, I've got carbon. If I've got 8 of those protons with 8 neutrons and some electrons, I've got oxygen. So there's a big difference between carbon and oxygen. And then if I just add 2 more protons and some neutrons and electrons, I get neon. So we wouldn't want to breathe neon very long, but we'd perfectly fine breathing oxygen. All it is a rearrangement of protons, neutrons, and electrons that makes the difference between oxygen, say, and neon. That makes the difference between any of these things, between hydrogen gas and gold. Hydrogen has 1 proton and an electron. Gold has 79 protons and a bunch of neutrons, etc. Now, most of the stuff around us is not just a single kind of atom, like all, say, carbon, or all oxygen, or all this or all that, but combinations of atoms stuck together. So here's some examples. In this diagram, black balls are carbon, or in some cases they look more like gray, but these are all carbon. Carbon is usually shown as a little black ball because carbon in its pure form, like in pencil lead, that's actually pure carbon. It's black. And the oxygen atoms here are all in red. So there's an oxygen atom right there. There's one right there. There's one right there. There's one right there. And then the hydrogen are all in white. So there's a hydrogen atom there and there. And then there's 4 of them over here. Now the thing to notice is this theme of arrangement again. So it's so important how these things are arranged. Notice there's only 3 different atom types here, or 3 different elements. There's carbon, there's oxygen, and then there's hydrogen, which is in white, and I can't draw in white, so let me draw in light gray. And of course, these colors have nothing to do with what the atoms look like. They're just to distinguish them here on the page. Color doesn't even really make sense at the level we're talking about. Okay, 3 different kinds of atoms, or 3 elements, but notice that they are in various arrangements. So let's talk about that now. When 2 oxygen atoms are stuck together, like right here, that's what we call oxygen gas. That's the oxygen that we talk about, like I need oxygen, or in an oxygen tank. It's the oxygen we breathe. So that's good old oxygen gas, or pure oxygen. And it's 2 oxygen atoms stuck together. Now, here we have an oxygen that's connected to 2 hydrogen. Guess what we call that? H2O. So now we have water. So you can look at oxygen in the periodic table and say, oh, that's oxygen, it has certain properties or whatever. But it matters so much how the oxygen is combined with other atoms in terms of what it's going to act like and what it can do in the world and how we respond to it. So put an oxygen with 2 hydrogen. You've got liquid water you can drink, obviously. We all know water. You stick 2 oxygen to each other, you've got oxygen gas that floats around in the air that we need to breathe. Over here, you stick 2 oxygen onto a carbon, and you've got carbon carbon dioxide. The villain that we hear about so much these days, the CO2 levels are rising. So at some point, maybe we'll talk about all that. But when you stick oxygen into a big old molecule, we call this huge thing a molecule. When you stick oxygen in there in this particular combination, exactly what you're looking at, then you've got sucrose, otherwise known as table sugar. So this is the white sweet stuff that we sprinkle on whatever we want to make sweet. So oxygen can be in different places, in different arrangements, with any number of other atoms and elements. There are just thousands and thousands of these combinations, and they're all very, very different. And it's the same with any atom. Here again, we can see carbon. Carbon is an atom that shows up in so many different places. Most famously, we call carbon the backbone of life here on Earth, because if you look here at the carbon in this sugar molecule, if you kind of trace it out, boom, 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 there's an oxygen there, but it's basically kind of forming the backbone of that molecule. So almost all of the molecules in our body, besides all the water, has a backbone of carbon. So sugar has carbon in it, protein has carbon in it, fat has carbon in it. But then carbon can be out in the air in a carbon dioxide molecule here. Over here, this is a molecule of what we call methane. You can see it has a central carbon atom and 4 hydrogen around it. So again, it really matters where carbon is, what kind of molecule it's stuck in. And even when carbon is just by itself, only carbon atoms, the arrangement of the carbon atoms matters dramatically. And this is mind-blowing. Diamonds and graphite, that stuff in pencil lead, are both pure carbon, nothing but carbon atoms. The only difference is that the carbon atoms in a diamond are arranged like this in sort of like a jungle gym, what we call a crystal structure, all linked together. And the carbon atoms in graphite are in these sort of sheets joined together, as you can see here. But both graphite and diamonds are just pure carbon. The arrangement makes a huge difference. So arrangement and pattern is so important. And most of the stuff around us is a pretty complicated mixture of various things like the oxygen gas, say, and water and CO2 and sucrose. Like a glass of milk, for example, is going to be mostly water. So it's mostly these particles right here are H2O friends. And then it'll also have some, not sucrose, but another type of sugar that looks similar to sucrose called lactose. You've probably heard of that. And then it probably has some molecules of oxygen gas floating around in there that got mixed in from the air. And then other things like fats and proteins and various other trace amounts of different chemicals. Now, how many, for instance, let's say water molecules? Well, a lot. All right, all these particles are incredibly tiny, unimaginably tiny. So, for instance, there are, say, in an average glass of water, I'm just ballparking this, there are about this many molecules of water. So that's a big number. I don't know what that number is, and I don't really care. Scientists would write that number as 7 times 10 to the power of 24, indicating that there are 24 zeros after it. So that's a nice, concise way to write that number. That's called scientific notation. So what's the takeaway in this video? It's similar to one of the takeaways in the first video. The arrangement of these atoms makes so much difference. In one arrangement, something can be healthy for you, for instance, to eat, and you need it. In another arrangement, that same atom could kill you if it's arranged in a different way, right? CO2 has oxygen in it, but you can't survive breathing CO2. CO2 has carbon in it, but we can't eat CO2, whereas sucrose has carbon in it, and we can eat it and get energy from it. So more on that later. That's it for part 2. Stick around for part 3. I'm going to start talking about chemical reactions. Very fundamental concept in science and in understanding so many processes around us and inside us. I'll put a link to the first video in this series here at the end of this video. You can just click on it, and then also, as soon as it's done, I will put a link to part 3 as well up here. There'll be links as well in the description below. If you'd like to get in touch with regard to tutoring, my website is up there on the screen. I tutor all levels of math up through calculus and down into basic math, 3rd, 4th grade level. I also tutor physics, chemistry, and biology, and SAT, ACT prep. Okay, see you soon.